Hello everybody and welcome to the Kemper Creative Learning Studio. My name is Denzel. We're going to have some fun with physics in today's live science show. Now earlier you may have received a bit of information to grab a couple things. I want you to go ahead and see if you can get yourself a balloon, a cup, plastic cup, non-breakable, especially because it may go flying, we don't know, and a small object like a bouncy ball that'll fit inside of the cup. So if you haven't grabbed those items, now's a great time to go ahead and get those. I'll wait about 10 seconds or so, and I'll entertain the rest of the guests with my juggling antics. Here we go. Antics. Hang on. Okay. For realsies this time, here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, that's physics. So let's begin. If you haven't grabbed those items, it's fine. You can still get them. We're going to start off with an amazing show. Now, at home, grab that balloon that you have. Because the first thing we kind of need to go over is the Newtonian laws of motion. Sounds very fancy, and it is indeed fancy. One of the things, or at least one of those laws of motion is this. Okay? We can sum it up as an object at rest stays at rest, an object in motion stays in motion. So take your balloon, grab it with your fingers, and hold it. It's at rest. Good job. Here, you can even make it at rest on the table. It's at rest. Excited. Okay, go ahead and pick that balloon up. Now let's put it into motion. So I want you to move it in one direction really slowly. Okay? This is an object in motion. It'll stay going that direction forever and ever and ever and ever until a second law happens. The second law says that objects can be acted upon by another force. Flip. Now, another force is going to be, in this example, a hand. So I want you to go ahead, grab that balloon again, take your hand and go whack, 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 whack. Perfect. Did you see the balloon doing anything? I should hope so. This object is being acted upon by another force, which brings us to our third law. Is this. When I apply force with my hand to this balloon, as hard as I smack this balloon, the balloon actually smacks my hand back with the same amount of force. Now, here's the final experiment. I want you to take your balloon, I want you to smack the balloon as hard as you can, and I want you to tell me if this hand of yours goes flying backwards away from the balloon. Here we go. 3, 2, 1. Goodbye, balloon. So did your hand go flying backwards away from the balloon? No, you're right. There's a couple of reasons why. Some of you might be saying it's because I'm so strong, and you are correct. You are very strong. You might even say it's because my hand has more mass, and that is something that we do with physics. So that whole thing about objects staying at rest and in motion and moving and forces can actually be expressed in the form of interpretive dance or in formulas. So let's go ahead and let's see if we can head on over to our screen for me to go ahead and put up the first formula of the show. Yes. Happy 20th birthday, Exploration Place. Let's go ahead and get rid of that. Boop. Our first formula of the day is going to be this formula. L equals R times P. You know what that means? Good, I don't either. It's alphabet soup. It's not really true. I actually do. You have these letters are representative of numbers. We can plug numbers in there in order to get ourselves a math equation. That's how formulas work. So for example, we'll take R. If we put this as a 2 and P as a 4, L would be 8. But what does that mean for me? Well, it means this. I like to put pictures in front of those. So let's get rid of those numbers and let's provide some pictures for it. All right, our first one is going to be R. Now, whenever you see R in an equation, I want you to think of a circle. But it's not really an exact circle. We'll talk about that a little bit later. But I want you to think circle every time you see R. R stands for radius. Our very first radius is going to be this amazing trash can. Okay? Now, here is my radius. I know you totally can see it. Let's try this. Here is my radius. Beautiful. Nice. Okay? we need the other components of our equation. We need to fulfill P, which is linear momentum. So help me to welcome my friend who lives inside of the box to the show. Say hello, friend in the box.
Enter box in play.
That's her way of saying hello back to you. She is very, very helpful in that she helps me explain linear momentum. So far we have ourselves a beautiful trash can, and we have ourselves our linear record player machine over here. Now, how does that help us figure out what L is? Well, I'm going to show you right now. Huh? It's cool stuff, right? Can you see it? No? I'm sorry, I forgot. The camera messes up the magic that's happening. It's easier for us to see air in the science studio than it is for you at home. There's something with the distortion of the lens. It's okay. I'll help you out. We need some fire for this part. Come on here, fire. Let's see what's going to happen here. All right, there we are. There we go. All right, let's put on our face specs to help us first. All right. Let's place the trash can back on top of our friend that helps us out. Let's add some fire juice. Remember, we're fans of fire juice at Exploration Place. There we are. Let's go ahead and light the fire. And I wonder if it'll be a little easier for us to see with lights down. You know, we really got to get it. Hold on. With the power of 2. You just gotta blow on it. Oh no! It's alright. That's what science is for. Okay, don't worry about it. I got it. We'll use the better one. There we are. Keep you over there. Alright. We have ourselves fire to help us see what's happening with the air. So let's go ahead and start up our linear momentum all over again and get this moving. Ooh, that's pretty cool. I like it. Yeah, that's really awesome. Yeah, I made it a special color just to kind of contrast with my blue self. So that's looking pretty good right there. It is indeed a fire tornado. So the example that we have over here, or rather the formula we have, ends up in this cool spirally fire that's occurring. Okay, the R is our radius of our trash can. The P is the momentum, the movement of our helper in the box. And, of course, the result is L, which is actually the way that the air is moving through the fire to give us that spin. Let's go ahead and get rid of that fire. Let's let it burn out. Move it to the side because I want to do one more thing using the same idea and concept. So let's say goodbye to my friend in the box. Goodbye, friend in the box. Let's go ahead and move our trash can and our fire back. Remember, we just lit this on fire, so I'm sure it's hot. Nice. Okay, move this down. And let's change something. We're going to change R, which is radius. Okay? So instead of us having the radius of the trash can, we're instead going to have the radius of these cool, clear tubes. Now this tube has been cut into 2 C shapes. And I need a little bit more fire juice. Fire juice. It's too much fire juice. I wonder if we'll get the same situation. We've changed our R, and we've also changed how our P is working too. But the result is very similar. It's very interesting how this is working. So before, we were moving with our friend inside the box, but we have no movement that's similar. We have no movement like this. But we do have similar movement of air. Our air that's all around us, when it gets warm or cold or chilled, it moves. So hot air inside of our column here is actually moving. Which direction does hot air go? It goes up, that's correct. As it moves up, cooler air gets pulled into the sides. They get pulled in from this curved angle. As they get pulled in on that curved angle, they manipulate the way that the fire burns, and we get that L all over again from our equation. So we have another way to make a fire tornado, which is really, really awesome. let's go ahead and turn this off so we can transition to our next formula. Let's cool that down for just a little bit. So, our very first one that we've expressed in the form of interpretive dance is that of L equals R times P. Physics, again, it can be expressed in the form of formula, but I like pictures. Let's go ahead and get rid of all that right there, and we're going to start our very next one. This next one is a favorite of a lot of folks. It's F equals M times A, or force equals mass times acceleration. So, interesting. I have a way to do this. Again, I like pictures. So let's do this. Okay. I need to figure out M. M stands for mass. And I happen to have a friend that's going to help me out with this particular one. Everybody, welcome to the stage, Victoria. Say hello to Victoria, everybody. Hello, Miss Victoria. Now, Miss Victoria, I need you to do me a flavor. Grape is one of them. Orange is another. I'm not fond of cherry. Ever so often. So I want you to stand upon this object. It is a scale, okay? And I'm going to take a measurement. All right, I was like 100 and some change. Will you go ahead and stand on there? Do you mind sharing, or do you want me to just keep that in my head?
72.6.
Hey, 72.6. Wonderful. We measure in kilograms here because it's a smaller number. It makes us feel better about ourselves. Exactly. We measure in kilograms because it's a better measurement for mass, which is M. So there's a 76 here. There's the trash. First try, as always. Move on over to this. Will you have a little sitsy, please? Thank you. Now, the chair we measured before, it's somewhere around 12 and change. But just for me, I'm going to say that it's 10, which makes us 82. M is 82. This will help me figure out what F is. F is force. We can calculate force. And I will be representative of the letter A. A. What? Safety? Oh. That's fine. There you are. I cleaned it for you. Sniff. Excuse me, I'm still riding the allergy train. I got another ticket today. I didn't want it, but they were like, you have no choice. It's great times. Here we go. Let's figure everything out. Remember, this is going to measure my F. I am representative A, and she is M. Are you ready? 3, 2, 1. All right, so let's see what we got there. That was pretty good. 1.6 kilograms of force. A is acceleration. I accelerated her. She was standing still, and I moved her. I accelerated. Okay, it's not what you expect. That's fine. Here we go. Let's do this one more time. Are you ready? For realsies, no fakesies. 3, 2, 1. Let's go. Let's go. Say hello to the balloon. It's gonna pop. No, it's not. Okay, let's see. We're up to like 6. Let's see if we can get you up to 7. 7. Perfect. We got 7, which is exactly what we wanted to have for our show. Oh, I'm sure she's fine. She'll be okay. Now, 7 is exactly what we wanted. So if we wanted to, we could plug in 7 here. We have the mass, which again was like 80 and some change. And if we do a division, we can figure me out, which would be great because I'm still working on what to do with my life. Now, no, I love doing this. This is awesome. Let's move on to the next one. I'm sure Victoria. Hey, yell, Victoria. You good? Thank you. F equals M times V squared divided by R. That's a good one. That's a good one, isn't it? It's fine. Here, I'll show it to you. All right, so hang on a second. Pictures. R. That's right. Remember, R is radius. Okay. When we think radius, we think of circle. A circle. Let's see. I could use a circle. Can I get a circle? Oh, thank you. Perfect. There we go. So we have a circle here. Right about here, please. Wonderful. Circle. So at home, do circle with your arms. Great. Okay, cool. Now I need to show you R. It's my friend R. Stay here, circle. It's great. So this is radius, the center point of the circle to the outside edge. That is our radius. We have radius, and then if you do 2 radius, that's diameter right there. And then this is circumference. We really just care about the radius part of it. Stay there, circle. Okay, so we have radius, we have mass, which we need mass. So we have my magic carpet here. Oh. Okay. We've got some water inside of a cup, and hopefully we can see how much water we have inside of the cup. Great. So water inside of the cup. Great. We have water. We have some mass here. Remember earlier we weighed that, and then we have this whole system of a lovely magical carpet for our water to ride on. Now, I'm going to spin this in a circular shape, okay? So we have the radius, we have the mass, I am v, that's velocity, and if we take all of that with a high-speed camera and a calculator, we can figure out force. But for right now, I'm going to send this water on a wild ride. Now, before I do, I want you to think. 1, the water will go splaying everywhere, or 2, it'll stay inside. How many of you think it's going to go flying all over the place? Okay, great. I actually saw some hands. How many of you think it's going to stay inside of this container? Great. Okay, here we go. 3, 2, 1. It stayed. That's pretty cool. That's pretty awesome. That's great. It totally stayed inside. Of course it stayed inside. For those of you that said it stayed inside, great job. You saw me put the lid on top of it. You did an awesome job with your eyes. Now, at home, we're going to do this very similarly, okay? So that and the ball that you had from earlier, I want you to go ahead and grab that. All right, let's see here. I have a few choices. So I was doing some experimenting myself. I think I'm going to go with the larger one right now. Okay, so take your ball. Perfect. Place it inside of your cup. Awesome. And now I want you to become a radius. So hold it down just like this. You see the circle? Hold on, let's do this instead. All right, you see the circle? This is the center point of your circle, your shoulder. I want you to begin to spin this cup around over and over and over again. Is the ball staying inside? Is it? Great. Okay, I want you to hold it straight up in the air and see if your ball falls out. Mine did it. Mine's magical. It's not magical. I cheated. Okay, I'll do it for real. I'll do it for real here in the studio, and you can do it again at home. Grab that ball. Go ahead and place it inside for real. I'm going to do a small one. Here we go. Inside the cup. Boop. 3, 2, 1. The ball stayed inside the cup. You did it. Okay, now, I am not going to ignore the water we did earlier. So now that you did it at home, now that you've seen that we can do it with a ball, I'm going to up the stakes. I'm going to place the cup on my magic carpet. I'm going to place this blue liquid inside of the cup, and I'm going to spin it on the magic carpet. Now, once again, I'll ask the question, how many of you think the water will go spraying all over the place, and how many of you think it's going to stay inside that cup? Great. Now, V, me, velocity, as long as velocity stays the same, it should work. 3, 2, 1. It's working. I haven't put blue all over the place. How are you doing, Victoria?
Great!
She's dry too. Look at that. We got ourselves a magical carpet ride with our blue water inside the cup, and it stayed in there. That formula ended up working out for us. That was awesome. That was awesome. You know what? Thank you very much, Circle. You can go ahead and head on out. Perfect. So we've seen force equals mass times velocity squared divided by the radius. These are kind of a loose example of those. Put pictures in place of those letters. But I've got one more for you. This is one of my favorites, okay? It's kind of a longish formula, all right? So in it, you can find one of these. You can find a, let's see here. You can find one of these and a multiplication. I think there's a T in there, some floating around in there. Oh, you know what? You know what else you can find? You can find like one of these K's, and then there's an A, and then there's this. Some of you recognize this. This is pi. Everybody loves pi, right? And sometimes there's a 2 in front of it. Sometimes there's some kind of stuff around pi. Pi likes hanging out with stuff. Okay, and then you reach a certain point where you start seeing triangles, like you start seeing pyramids. Like pyramids show up out of nowhere, and you're like, oh. what's this pyramid mean, right? And then Z show up, and then there's this Disney symbol. It's like, woo! It comes out of nowhere. You're like, where did you come from, Disney? And then there's there's this really big kind of F-looking shape that sort of shows. And then you reach a certain point where you're just doing unlimited sigma, and unlimited sigma, you've gone so far out of it. It's just ridiculous when you go unlimited. But it's fine. You know what? It's fine. I have a picture for it. I keep it safely behind my carpet. The carpeted area is right here. Yeah, some of you know this. If you don't know this, it's what I call a vortex ring generator. Okay, here we go. I'm going to aim straight at the camera, and you tell me if you can see what it's doing. 3, 2, 1. You see it? Hold on. I'm just going to shoot it all around. Here we go. You see it? Did any of you see it? No? You can't see air. You can't see air. Hold on. Let me think about this for a moment. I forgot about the distortion of the lens. Oh, the circle. Can I get the circle to come back down? It has magical properties, okay? When it has magical properties, we call it a hoop because, hello, other organized people. You have a hoop. Now, through the magical hoop, let's get it spinning just a little bit here. Through the magic of the hoop, we can go ahead and actually see what I'm talking about. It's the hoop's properties. Are you able to see the vortex rings? Maybe, sort of, not so sure. I tell you what, hoop, why don't you head on out here, bounce on out here, because it's not really magical. All you need is just a little bit of distortion and just the right amount of light. So we have a certain radius that works here. We can adjust that radius. We've been talking about radius this whole time. Remember, radius all over again. Let me adjust the radius one more time. Hold on. Okay. All right. There we go. Let's see. They're so small and tiny. It's hard to see. It's okay. It's not you. Again, that's the camera. It's fine. I have another way to show this off. It's fine. Okay, here we go. All right. Magic is in the smoke. Yeah, you're right. It's totally in the smoke. All right, so what's a vortex ring generator? Well, this whole time, I've been using some properties of air. Okay? Velocity, the movement of the air. I've been forcing air to go straight out of my devices. Okay? As it moves straight out, it collides with standing air, and it begins to roll back upon itself. Okay? So you have moving air punching its way through standing air, and it begins to roll back. As it does, it creates a toroid. Yeah, toroid is it's a donut. Okay, that's what it is. Now, we can adjust the size of this toroid by adjusting the radius, and also we can adjust the way that it moves by adjusting its velocity. So we're going to roll out a very large toroidal vortex generator, and we should be able to catch this on camera much easier than the others. See if I can get one towards the camera. There we go. Amazing, right? So it's a very stable arrangement of air molecules that gives us this toroid. We've seen all kinds of ways to express the Newtonian laws of motion in formulae. Now, don't be afraid that your numbers will eventually turn into letters, as long as you know how to put pictures behind them. This has been Fun with Physics, everybody. Thank you so much for checking us out. I hope you have fun with the rest of your day. Go ahead and stay safe, have fun, do some physics experiments at home. My name is Denzel. I'm hiding in the smoke. Have a wonderful rest of your day. Thank you so much for watching.